Okay, now today we'll be learning about nuclear physics. Nuclear physics is all about nucleus of an atom and how an atom comes into being, or what keeps the atom together, especially a nucleus together. Now, there's a point to think about. Atom is very, very small. It is like way smaller than what human eye can see. The, the problem in looking at a single independent atom, is not that we don't have a powerful microscope. The problem is that atom is so small that a wavelength that can actually strike a single atom and bounce back is 10 to the power minus 10. That is way smaller than the human visibility range. The smallest wavelength we can see is 410 to the power minus 7. So atom is smaller, and the wavelength that can actually strike an atom and bounce back is not visible to human eye. But the nucleus is way smaller, around 100,000 times smaller in diameter than atom. And that is the region where all the protons and neutrons are together. The question is that if that is the teeny tiny space where all the positive charge is accumulated, don't you think when we bring positive charges close to one another, they should repel one another? They have a natural built-in hate for one another over there. So if they're pushing one another away, what keeps the atom together? Answer is binding energy, strong nuclear forces. These forces are a reason of binding energy, and binding energy is energy that is keeping an atom, the nucleus, together. Where does this energy come from? This is an example. Obviously, we don't have these kind of scales that can measure protons and neutrons, but just a model. Okay. Now we have two electronic balances over there. In one electronic balance, we can see 4 protons and 6 neutrons. These blue circles are protons. These are neutrons. Now, protons and neutrons are separate, just like not formed into a nucleus. Now we put those 10 things on the electronic balance and measure it, and mass is M2. Now we have a nucleus that has 4 protons and 6 neutrons, and we measure the mass of that nucleus. It is not important which nucleus is there, just a nucleus. And this is true for all the nuclei over there. The strange thing is, we expect that the mass of the nucleus and the mass of the nucleons should be equal. But that is not how things are. The strange thing is the mass of nucleus, which has 4 protons and 6 neutrons, is less than the mass of 4 proton and 6 neutron. Like the separate mass is more, and when they form nucleus, the mass decreases. What happens? Mass converts into energy. This is the energy that is used to keep the nucleus together, and this is also the energy. If you want to separate all the, like, listen, the protons and neutrons are forming nucleus, and now I want to make them separate protons and neutrons. The thing is that some of the energy has been converted to mass. Now I need to provide that energy to the system, so protons and neutrons can gain back their mass and get separated. So binding energy is not only the energy that is keeping the nucleus together, also it is the amount of energy that we need to supply to the nucleus to completely break it into its components. So protons and neutrons are staying together because of sacrifice of their mass. Mass of nucleus is always less than mass of nucleon. The difference between the masses is called mass defect. And if you want to know how much mass is being converted to energy, and how much energy that mass is producing, and that is the time when we take help from the famous Einstein equation, E equals to mc square, where m is mass defect, which makes binding energy. Binding energy is the minimum energy required by the nucleus to completely disassemble it to its protons and neutrons with zero kinetic energy, and they are at infinite distance from one another. They are completely separated. There is no uh, connection left between them. The minimum energy to do that is called binding energy, because this is the energy which protons and neutrons need to gain back, convert back into their masses, and get back their mass and become separate protons and neutrons. Now, we harvest that binding energy in different forms, and there is a method that is naturally done, that's called nuclear fusion, and there's a method called nuclear fission. Fission is a man-made process, and in this process we fire a slow neutron on an unbalanced nucleus, and we break the nucleus into daughter nuclei, plus some extra neutrons are they come out, and those new neutrons, they perform the same process on the next atom, and then next and next, and this is a chain reaction, and there are some conditions that we need to fulfill to keep this thing happening again and again. In nuclear fusion, smaller nuclei, they get together and they form a bigger nucleus. In both cases, the mass of the original thing is always more than the mass that is being produced. There's always some mass that disappears. Some of the mass goes away, and that mass that is reduced, the mass that disappears, that mass converts into energy. And this is how we harvest energy in different ways. In nuclear reactor, we do nuclear fission, and in naturally on stars, nuclear fusion is taking place to produce energy that we can um, experience, that we can see. Now, this is very simple. Mechanically, if you think that okay, uh, some matter can fuse, some matter can fizz. So which nuclei are supposed to fizz more than the other, and which nuclei are supposed to fuse between one another than the other? Now, answer is smaller nuclei, they have more tendency of getting together. Smaller the nucleus is, they have more uh, tendency of getting fused together, and larger nuclei, they have more tendency of breaking into smaller ones. I think that should make perfect sense, because bigger nuclei, they will have like, or they already have a very big nucleus, and to, to get bigger will be a problem for them. Smaller nuclei cannot get more smaller, so they tend to become bigger. So here we have the graph of atomic number and binding energy per nucleon. You see that barium and iron, they are on the top because they have maximum binding energy. So they are the most stable things here around us, barium and iron. Now, if an atom or nucleus is smaller than them, they have more tendency of fusing together. And if an atom is bigger than this, then bigger than barium and iron, then those atoms are they have a natural tendency of breaking into smaller nuclei if we bombard them with slow neutrons. So this is the graph, and this region, the whole region, is more stable region. And after a certain value in this direction and a certain value in this direction, the process becomes easy, or the instability increases. But in the top region, they are the stable nuclei, and we have a lot of them. Now, just let me add small notes over here. Nuclear fission. A slow neutron is fired on an unstable nucleus. The large unstable nucleus breaks into smaller nuclei, and energy is released. This energy is used in atomic bombs for destruction and in atomic reactors produce electric energy. This is a man-made process, so requires human intervention. Now, the problem is that the neutrons that are released in this process, they are not slow neutrons. They are very fast neutrons. So, in order to perform nuclear fission, those neutrons should be slowed down. This is where the nuclear reactor comes in, and that nuclear reactor performs its job to slow down. It absorbs energy of the neutrons, like subtracts kinetic energy from them. They slow down, and then they can hit other nuclei and can perform nuclear fission again. So, in order to keep this process continue, we need to intervene, and we need to uh, change the kinetic energy of the neutron. But nuclear fusion, once we start nuclear fusion, then this process keeps happening itself. It keeps happening again, happening by itself. We don't need to intervene into it. This is a natural process. This is why nobody goes to sun and refuels it or do something over there. So the process keeps going. It is going on by itself. It is totally stable process that is happening by itself. Now, radioactivity. What is radioactivity? Larger nucleus, and I put a cross on the table over there. Larger nucleus that tend to they are considered to be unstable, and they are continuously converting from one to another and another to another. They cannot stay what they are. They keep on releasing some of their content, and they naturally keep converting from one to another. That's why we call them unstable nuclei, because they cannot be what they are. They continuously change. So what is happening is sometimes they emit alpha particle or beta particle. Their complete uh, uh, explanations of these things, they are in AS. We don't need to go over there. Just to recall what was happening over there. Sometimes a whole nucleus becomes unstable, and nucleus converts from uh, uh, nucleus wants to gain stability. So in order to gain stability, it emits some of its particle. So the particle that is normally emitted by the nucleus when the whole nucleus is unstable is a alpha particle. And alpha particle is a nucleus of helium, which is released from the nucleus of unstable nuclei. And in this process, along with the helium nucleus, some energy is released. And when any particle, any nucleus releases its protons and neutrons, it cannot stay the same nucleus. I hope you understand that we differentiate one nucleus from the other on the basis of its proton number. And when anything is emitting two of its protons, I hope you can understand that it will not no more stay the same element. Its element will change. And see, this is happening over there. There is an element X with atomic mass A, atomic number Z. When it emits an alpha particle, its atomic mass becomes 4 less. You can see Y has A minus 4 on top. Y has A minus 4. So it means the mass number has been decreased by 4. But that does not change the element. Same elements can have different masses. This is they are called isotopes. But look at the bottom. There is a proton number. The new proton number is 2 less. That is the game changer. That is what is causing the problem. That is why we do not have the same element. We now have a nucleus of a different element. So whenever any element emits alpha particle, it does not stay the same element. It becomes some other element. Now, depending on what was the original element, and we can see if it emits two protons, which new element it can come and become. And we can figure that out from the periodic table. Now, sometimes it's not that the nucleus has become unstable. It is that a single nucleon becomes unstable. So when a whole nucleon becomes unstable, then it is not the nucleus that converts into a different nucleus. It is that nucleon converts into a different nucleon. Proton converts to a neutron, or neutron converts to a proton. Whenever this is happening inside the nucleus, a proton is converting into neutron or neutron is converting into proton, we say that beta emission is happening. Beta particles are released. And either a proton converts into a neutron or a neutron converts into proton. And again, I think you can see that proton number will change in either case. Whether a neutron becomes a proton number should increase by 1, or a proton becomes a neutron, in that case, proton number should decrease by 1. In both cases, we will have a different element. The nucleus will belong to a different element. You can see X is emitting a beta plus particle, and C, its proton number is decreasing by 1. And in the second case, a beta minus is emitted, and you can see the proton number has increased by 1. In both cases, we now have different elements. So this is how alpha particles and beta particles are released, and emitting alpha particle and beta particle by emitting alpha particle and beta particle, we can the nucleus number can change, and different element can come out. Radioactivity is a process, and this process depends on how many radioactive nuclei are there. So activity is directly proportional to number of radioactive nuclei. A equals to lambda n. What is A? It is the activity measured in Becquerel. Becquerel is very much same as frequency per unit time, and number n is the number of nucleon, has no unit, and decay constant has same unit as activity per second. Now, when any radioactive nuclei, they are converting into something else, we can see that the number of original radioactive, the mass is same. You can see that the size of the sample is same, because it is not that those nuclei are disappearing, they are converting into some other nuclei. So they stay there, but they are now no more the same nuclei, they are some new nuclei. Activity depends on number of radioactive nucleus. So there will be a time when half of the number is there. So what should happen to activity then? When number becomes half, activity also becomes half. So this is a process that depends on number. That's why when number will be reducing, activity will be reducing. So the amount of particles that are converting per unit time will change. So if it takes 10 years for something to reduce from 100 to 50, in next 10 years, it will not convert to 0, because the process is not happening at the same speed. It is happening on half of the speed now. So what will happen? In first 10 years, if 100 becomes 50, then in next 10 years, 50 will become 25. It is not that it will become 0, it will become 25. Why? Because the activity is also slowed down. It is not happening at the same rate. Activity is also happening at a lesser rate. Now, radioactivity has two properties. Number one, it is random. When we say random, it is not that activity may happen or not, does not happen. No, 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 no. That is not random. Random is that if there is a sample, we cannot predict that which nucleus will perform radioactivity next. For example, if you have a rock of uranium in your hand, you cannot predict that which nucleus, whether it will be a nucleus on the surface, it will be a nucleus in the center, it will be nucleus which is warmer, which is colder, which is wet, which is dry, which is under high pressure, which is in vacuum. You cannot predict which nucleus of uranium will perform radioactivity next. That is what is meant by the phrase random. Radioactivity is random, and we cannot predict which nucleus will perform radioactivity next. Spontaneous. Spontaneous means, and now it apparently feels like it means that happening suddenly, but that is not the case. Actually, spontaneous means that it will happen no matter what. Will happen no matter what. This means that radioactivity is completely independent of any physical change or any physical condition around it. You cannot speed the radioactivity up by heating the sample or by cooling it, by putting it in water or putting it in vacuum or in high pressure or very cold nitrogen. There will be no effect of any physical change on the performance of radioactivity. It will happen if it is slowing down, it will keep slowing down. If it is increasing, it will keep increasing. If it is happening 10 units per second on a certain amount of time, it will keep happening with that rate without any change. Now, when we make a radioactivity graph or radioactivity sketch, this is time, this is number. The graph is like this. Why there is this fluctuation? Fluctuation is because of the random nature. And why it is following a certain fixed pattern of slowing down over time? I hope you can see there is fluctuation, but overall, there is a trend as well. Fluctuation is due to random nature. Fixed trend is due to spontaneousness. There is a trend. There is a trend that radioactivity is decreasing, and that trend is because of spontaneous nature of radioactivity. So we'll do the radioactivity formulas tomorrow, and we'll discuss half-life. And after that, we will be able to solve questions. Okay. See you people tomorrow. Allah Hafiz.